Okay, let's see if this is actually going to publish this time. I just waffled on for 10 minutes in a private live stream, which no one saw. But I think we're back live again. Let's do a double audio check there. Good. So, this is a so-called POWERCUBE. This is one of my 45 amp variable power supplies. And this used to be, I believe, the grid power supply for a 50 kilowatt Itelco analog TV transmitter. So this was feeding the grid current to a ridiculously giant 50 kilo RF transmitter tube. In their original configuration, these things have no display, no output plugs. It's all loomed in the back, and all they do is you plug them in and they put out 5.0 volts, and that's what they do until you turn them back off. Now, when the TV transmitter was dismantled a few years ago after sitting idle for many years, I, of course, got my hands on two of these, and I saw the potential and rebuilt these chassis to house them as a variable power supply, because they're built around a couple of fairly standard issue DC to DC converter bricks. What's underneath this big heat sinks is like two giant packages, and they're very clean output and very flexible. These can put out about 1.5 to 15 volts, and you can adjust them on this potentiometer. Now, to do that, it took a fair amount of modification to both the backplane in here and to the boards themselves. And most obviously, you can see this guy has a fan, whereas this guy, who's basically an original, does not. So if we turn this on now, this has a third board inside. I have a few spares. You can see that it turns on, the display lights up, we get a voltage and a current reading. And if we take a fat wire, just shove it from negative to positive, it'll scream to life, and we can adjust our output voltage and feed up. We're putting out 47 amps through this cable right now. If we keep that up for long enough, it's probably going to go on fire. So I really love these power supplies, and they're very useful because, for instance, if I need to charge a single cell down in the basement, one of my 2-volt lead acid batteries, it's very handy to have a 1.5 to 14 volt power supply at hand, which can put out, almost 50 amps. But recently, or not so recently, but recently it has started to bother me. This board has gotten a fault, and we might be able to show it to you on this camera. If we just lift it up there, let's see where we are. It would be that fuse there, right in the center frame, is very black inside, and that's because it's blown. And that's because these modules, they're built up around two Ericsson branded DC to DC converter bricks. It's basically two giant, completely integrated modules underneath this heatsink, which basically they take in rectified 230, they spit out the DC, they take care of capacitance, they take care of inductors, they take care of everything. It's literally DC in, DC out. You don't need any supporting components. All this other stuff is basically optional. And one of the DC bricks in this module has failed. I could order a new one, put it in there, or I could take module from this one and put it in there. But I figured this board still works just fine at 20 amps. There's no reason to really change that, since I have a few of these spare boards. And last night I took another of the spare boards, I have two spares, and just did all the modifications to it, put it in use in the other chassis, so I already have all the boards I need. But in case we have another failure, it would be handy to just have this guy as well, pre-converted and ready to go. Because since this is a stock board, completely original from how it came in the TV transmitter, if I shove this in the chassis, it will work to the extent that it will put out exactly 5 volts, and it will do that. somewhat to my detriment, I might as well show you. These guys have terrible capacitor discharge, so we're going to be working with a bunch of voltage in these big caps. There's voltage in those big caps right now, so I need to be careful not to prod around too much. But if we rip this out, we get another board. This is the one I modified last night, because it has a different cheapo 120mm fan there. So we'll put that aside, somewhere off camera, far away. And we'll shove this unmodified board, completely Itelco original, I think. It has some jumper wires, but it should be mostly original. And just shove that in there. And turn it on, and we'll see what happens. In you go. So if we turn this on now, we have no display. And if we take a multimeter, prop that off there, in a way where you preferably can see the display. I think we get exactly 5 volts. Okay, we get... Oh, this one actually has... right, this is a slightly modified board, it seems. So we actually have a voltage regulation tacked onto this one. I forgot I'd done that. So this one probably just is missing the display options. There we go. It's probably also got an OVP issue. Let's see, I think this is the board where if you turn this up too high, it'll just shut off. So we'll just turn this up, and I think it's just going to basically cut out. Yeah, there we go. So if we try to max the output voltage, this board will actually shut down. So it does have an issue, even though we do have adjustable output voltage. You obviously want to be able to max out your potentiometer without your power supply shutting down. Because another rather annoying issue with these guys is that the time it takes for the OVP to reset is like 5 minutes. So if I were to turn this on again now, we'd just have no output. We'd have to sit around waiting forever for anything to happen. Last night I was reading the schematics. I think I figured out how the overvoltage protection works. I'm not entirely sure, so we're going to find that out. But in essence, we're going to be just copy-pasting a few jumpers from this board onto that one. And we're going to be putting a couple of zip ties on this guy. Ah, bloody hell. See, I put these zip ties on here for a very good reason, and that's because if you want to rip this board out after it's been on, we have rectified mains in those caps, and I have to wrap my finger around this tiny little screw and try to rip this out without getting 325 volts DC in my fingers. Right, so I think this wire is what enables us to have voltage control on this board, but given that everything else is original, I don't think we have any more modifications, except that I have removed a TL431, which was doing over voltage protection. That's basically all the changes. We also need to just do the drudge work of replacing all these ancient capacitors. I think these boards were somewhat old, even in 1997. People are showing up in chat. Good, I was wondering if it was broken or not. Tony Ganner asks, did you discharge those capacitors first? That's done through this resistor and this LED. But we probably have like 100 volts in these guys still. It'll slowly bleed out over a few minutes. But it has annoying voltage in it still. But let's just get these guys under the microscope, see what kinds of differences we have here. I can see that we're missing at least one jumper wire. And we're this board is very burned in a place. I can tell you a story about that in a minute. Let's get the microscope up on the big screen. Let's get them. Whoa, hey, it's even working. That's unusual. No technical difficulties. So, if we take a look at the modified board first. Oh man, we are way too zoomed in here. But this is by the backplane connector, so let's grab a poke a bit. So this is the backplane connector. We have the bumblebee wire going to that pin. We have this wire going to that pin. I think that's a 12-volt supply or something. And we have a couple of small capacitors mounted here across the output. And we have a component removed in this very burnt out part of the board, which is going to be necessary. If we go to the unmodified board, you can see what we have, a wire and a component in the burned part, and we are missing a wire here by the backplane connector. So we might actually, an amazing thing about this is that I actually have a schematic for these entire boards, including the control boards. So we can take a look in the schematic and get an idea as to what we're about to do. Wow, that is completely overexposed. I'll leave it on auto for the time being. So let's see if I remember right. I think this, it was the filament power supply. That's what these guys are. Let's have a closer look. Filament power supply. Yeah, the grid power supply. That would be very high voltage, I think. I'm not too keen on valve stuff. Right, so let's have a look at the documentation. And what we are concerned with is going to be so this is the control board, the mechanical drawing. We don't care about that. We care about this is the control board schematic. So let's have a look at what we're dealing with. I hope that's reasonable resolution on the stream. I can't make it any much bigger without turning it into a big mess. This control board basically controls the two power modules and adjusts the output voltage and handles a couple of fault conditions. Tony Ganno in the chat asks, how much was your microscope setup? 1,500 euros, give or take. So what's causing the board to shut down, I think, when we turn it up too high, is going to be this circuit here, which basically is just an error checking circuit to make sure that there's not too much current going out and too much voltage. So we have a few pins here. This guy is labeled filament. I think that goes to our output voltage, and that goes through a resistor into a potentiometer, and then it goes and integrates with what's coming in on pin 16 here, which is our current shunt. So these guys go together here, get mixed and get fed into the negative input of this op-amp here. I think this is set up. I haven't actually confirmed any of this. I've just twiddled the potentiometer and it seems to work. I think what's happening here is either an over voltage situation coming through the potentiometer and this resistor, or an over current situation coming through this resistor here. It will make this op-amp switch states. There's some kind of circuitry there to make it latch, and then it just feeds through the rest of this error thing. Goes through the optocoupler and out the fault output there. And I think the reason this thing takes so long to reset is that there's just a fair bit of capacitance and not a lot of stuff that actually uses power. And I think it might be triggering a fault condition on the actual bricks, the DC bricks here, and they have the giant big primary side caps there, which just take forever to discharge. So to get rid of the overvoltage issue, I think all we need to do is twiddle this potentiometer. I think that's all there's to it. I haven't really confirmed that, but we'll give it a go. So to modify the voltage regulation, which has actually already been done, we can take a quick look at this part of the schematic. So this weird looking circuit is called an ISO 122, and it's a real oddball of a thing. It's called a, an isolating amplifier. And this is basically a capacitively coupled, a high voltage isolation circuit, kind of like an optocoupler, but it's more high-tech and a bit more linear. It acts like a galvanically isolated unity gain op-amp, basically, with its inputs here and its output here. And you can see in the original configuration, this is the voltage adjust input on the control board. You have a voltage adjust signal going through a resistor, going to a TL431, which is just acting as an input voltage limiter, and then feeds into one of the inputs of the op-amp, and the adjust signal goes out there. So by feeding a variable voltage in here, we're just adjusting the output, because this pin then goes to the voltage control signal on the big DC bricks, which are actually used doing all the heavy lifting. And basically all I've done here is remove this TL431 and replaced it with basically a couple of resistors to make the input impedance of the voltage adjust line here more compatible with the potentiometer I used there. So literally to adjust this thing, we feed a variable voltage between 0 and 12 volts in there, and we have an adjustable power supply. Now there's a bit more stuff going on the actual power board though, and that's something I haven't really, that's just a mechanical drawing, that's something I haven't really dug into too deeply. It was years ago I did this modification, and I frankly don't remember what I did, but we can take a look at the schematic anyway, just for the fun of it. I really hope this has enough pixels to go around. So this is the schematic for the main board, the big PCB, this whole guy. And it's a, as you can see, it's a very simple circuit, because all the heavy lifting is being done by these two DC to DC integrated converter bricks. Now, this is a split system. I think VCore is the company who makes these now. They seem to actually be a kind of current model. This is a 261EU driver, and this is a B61EU booster. And these seem to be putting out about 20 amps at 0 to 15 volts each. And the input circuitry side of this is incredibly simple. We just have mains coming in here, fed through an internal 50 Hz isolation transformer in the chassis. You can't see it, but there's actually a 500-ish VA isolation transformer in here. So these bricks don't actually provide galvanic isolation, or if they do, it's not enough for the application of the mains voltage to 30 kilovolts, which this thing actually saw in the TV transmitter. But anyway, we just have basically 230 volts going to a rectifier, going to the big capacitors, which would be these guys here. And then there's a couple of fuses, fuse there going to driver 1, fuse 2 going to driver 2, and then they have their outputs combined somewhere around here. Let's see, this is the positive output, and this is the negative output. So we see negative going to ground, we have a current shunt on the negative side, and here we can see we have, yeah, this is going to be output going there, and oh man, this is a bit messy. Where are they actually combining? It doesn't matter. The outputs of these guys are just combined. Some of these lines are going to have appropriate balls on them to work. One modification I had to do to make this thing adjustable, since it initially was supposed to never go above 5 volts, because 5 volts was a fault condition, it would destroy your extremely expensive transmitter tube. So they had another TL431 redundant on this board, which was just mounted on the back of everything. That used to go on a few of these pins in this area. You can see that they've been soldered on. And there used to be just every board had a TL431 there, just to limit the maximum input voltage going to the driver DC bricks. So that's just been removed, and that enables us to actually get the higher voltage out of this thing. This is where we're getting to the part where I don't really remember what I did to these boards back in the day. But some of these jumpers around here that we're going to see on the board, it's basically just a jumping output adjust from the control board to there, something like that. I don't remember. It just works. It's just super simple, like one jumper wire. And then all I've done aside from that is basically replace the capacitors to make them a bit more reliable. And I think that's basically it. We can take a look at the hardware now. I do love it when I get proper schematic with my stuff. It feels like cheating when you're used to just not having any schematics for anything ever in today's repair hostile world. So we can see this is the control board. We can just take that out and have a look at the modifications which have been done to it. Since we're going fairly in depth on this anyway, this just rips out. So let's bring the schematic back and have a board of a schematic at the same time. See if I manage to figure out what's what. I have a few extra schematics for like other boards from the transmitter in this, which have been saved for various fun and exciting reasons. Is this the control board? Yes, here's the control board. Let's zoom down a tiny bit just to make it a bit easier to see the actual board. So this is the out of frame. There we go. This is the ISO 122 isolation amplifier, and this is impossible to hold in place. That's what you use your several €100 multimeter for. Right, there we go. So this is the APA 122, and these resistors here, you can see we have a couple of bodge resistors sticking up from the board. I think one of them is replacing R42 here, which used to be a surface mount resistor, I believe there, and this R42 has just been removed because we have a fairly high impedance in the control circuitry I constructed for this. So R42 being a 470 ohm resistor, it just kept pulling it low. So if I didn't remove R42, we'd just never get any voltage out of this thing. And that's been replaced with, I think, a 27K resistor. And R44 here might be jumpered with something. No, it's not. We might actually do that if we don't get enough voltage out of this thing. R44, it's a star here. It's 1K on this board, and it's this guy down here. And that one is just a series resistor. But for some reason, it actually has a fair bit of voltage drop across it. So if we get into like 14.0 volts out of this board, we might just jump that basically. And what more? There's really not much more being modified on this guy, actually. That's basically it. Remove the TL431 and put these resistors in its place. I think some other resistors has also been removed. You can see there are pads there which have been soldered on. But it's basically all to do with making sure this input has the appropriate resistance to be fed by my 10-ish K potentiometer on the front here. But I don't think we need to actually do anything to that board, because the issue we will have with making the board work with the rest of the chassis is we're missing the power supply for the meters, and you obviously want to have a power supply for your graphic meters, so you have some idea what you're actually putting out. And I think that's just to do with literally one jumper wire. So this is going to be an incredibly theoretical episode where we just talk for half an hour, solder one wire in place, and then everything works. But hey, theory is fun sometimes, so let's just put these guys next to each other. Man, I wish I actually had this in widescreen now, but oh well. Can we work with that? My bench is not appropriate for this. So let's see what we have. So this little jumper wire is missing. We have the bumblebee on both. We have this actual factory wire on both. So I think we're literally just going to be putting that wire in place. Nothing more to it. Oh man, we're zooming into all the wrong places. So we have this guy on the second pin from the right. Let's just get the same green jumper wire that I've been using for 15 years by now. Literally the same roll. And take a little bit of the insulation off and solder it in place. By the way, these side cutters, Giacomi from Italy, buy these. These are the best bloody things ever. I bought like 10 new ones recently. It was a shit ton of money, but so worth it. I've had my previous one of these I bought like 10 years ago and I still have it in use. I just bought a few new ones because like Knipex and other brands are just complete garbage compared to Giacomi. Hot tip right there, if you're European at least. They are expensive here. They're probably even more expensive if you live further away. So perhaps then you want to look at some other brands. Some solder water on there. I have completely the wrong tip on this for this kind of work. Let's put a not ridiculously oversized tip on there. I was so clever, and I preheated the iron prior to starting the stream and everything, and then we have a wrong tip in. Can you smell the name again of the cutters? It's Giacomi. Pierre, as in a Pierre, Giacomi. Pierre Giacomi. It's weird. If you Google Pierre Giacomi, you'll find them. TME has them. TME.eu. This particular model is called TR25. I also have a couple of others. We have the all-round ones, which is the TR30. This one has the lead snipping add-on, which makes it so that your leads don't go flying. This is the TR20 with its little cute hearts on. This is just the tiny one for just reaching into super difficult to reach places, like you have a wire inside a hole. Absolutely beautiful. Rather special purpose, but I do not regret buying that. And this is the TR25, which is just it's really all around, absolutely lovely. Again, I've been using one of these. It's actually a TR30, but I've been using one of these for about 10 years. If you look back on basically every live stream I've done ever, you will have the same POWERCUBE TR30 in every video. It's insane how long they last, and I still have it. Anyway, I think our iron's hot now. So we want to do second pin from the right. Just add a tiny bit of solder on there. Tiny bit of solder on the wire as well. Like so. We want to snip the very tip off of this, and I want to not use the TR30s because they have the non. They have a little attachment. I have a tiny little tip there. We can just poke that on. Like so. Now we want to use some tweezers to shape this. I can't really get everything in frame for you. Sorry, I wish I had infinite pixels for you, but I don't. And we want to just bridge that to this other lead, like so. So we'll snip that at reasonable length. And I should have stripped this before I actually shaped the lead, but oh well. We'll make do. It's so nice to have new sharp side cutters. When you've used the same ones for 10 years, you just don't notice how dull they get. Even though my old ones aren't that dull because POWERCUBE are amazing. There we go, that's nice and stripped. Turn that, poke it onto the other one. So I want to shape that so it doesn't actually press up against the other wire, because that's the point of failure. And we want to put a bit of fresh solder on the joint as well, not just the cable. There's a tiny bit of fresh solder there. And prop that down. There we go. I have no idea what that wire does. It's been almost 10 years since, well, not 10 years, but like 5 years at least since I did actually figure out, yeah, I need a jumper there. And I have no idea what it does. I think it's like taking external, maybe. It might be. I think what this, no, it can't be, because this board actually works without this wire. I think it has to be the bumblebee wire. I think that's feeding power to the adjustment potentiometer, because we had no external adjustment capability before. That's something I've added to these boards. So that's probably what the bumblebee wire does. There's going to be some funny business for this. It's there for a reason, I know. Maybe it's the power supply for the meter. And actually, it almost has to be the power supply for the meter, since we're not actually going to do any more modifications to this board. The rest is really just going stupid and swapping out all the old components. So I think if we just put this board into the chassis, we're actually going to see the meter light up. Place your bets. Although we of course need to actually get the control board back installed. Well, let's just do this and test our hypothesis. I'm quite sure the meters are going to light up now. Actually, before we do that, let's adjust what I think is the over voltage protection circuitry, so we're not quite going to get to see it light up yet. So this is the potentiometer we saw in the schematic next to the what's it, OP122, is that the right thing? the ISO 122. And this is what's going to be adjusting, I think, the over voltage protection threshold. Now, if it does something else, we don't want to forget what it was doing. So we're going to take a measurement of what that potentiometer is actually set to right now. I'm going to fetch a good pen, and we're going to actually write down the resistance of that potentiometer, just so we can go back, just so we have so we have a Control Z if we need it. So these 3 pins are the potentiometer we're looking at, and let's just measure the voltage. Now it's connected up so that these guys are actually in parallel. We don't care about them. We just want to measure between there, 7.1k. So we'll just write that down next to it, just so we can go back if we need to. Oh, I'm about to ruin everything. Micro writing. 7.1k between there and there, like so. Now we remember the 5th of November. No, we remember our pre-adjustment potentiometer setting. So I think the way these usually work is they have a little brush that if you tighten it, you get the brush moving that way, and you get lower resistance between those two. If you unscrew it, the brush moves that way, and you get higher resistance there. Since this resistance is what connects our output voltage to essentially the alarm, the fault trigger, we want to raise the resistance. So we want to turn this counterclockwise a few turns. We don't need the OVP at all. If it were up to me, we'd be constructing an ideal power supply, which would just go up to infinity volts. But sadly, we're not going to be getting more than about 14.8. So now we have 10k. It's really maxed out. So, if my theories are correct, we will now basically be done with this, and all that remains is going to be to do the drudge work and replace all the electrolytic capacitors and stuff, find a suitable fan, which I won't be able to do now because I'm out of 120mm fans at the moment. Let's get you guys a better angle for that. There we go. Beautiful. Let's actually be clever and put a bloody zip tie there so we can rip the board out without getting 300 volts DC in our fingers. Let's just remember to do that. Small zip tie. Now this is one of the most difficult parts of this job, because we need to not tighten this zip tie. It's so extremely tempting to just tighten this up, but we want it to be a loop, so we just want one single click. Click, click, 2 clicks. We have an untightened zip tie, and I'm going to cut the tightening thingy. There we go. So now we actually have a little grip to rip the board out with. Right, let's see if the meters are going to light up. Plug in. There we go. We have meters. Let's see if we can actually turn this up. 6 volts, 7, 8, 9, 10, 11, 12, 13. Ah, it's still triggered. So this board probably is going to keep having that OVP issue forever. Ah, that's a disappointment. I actually have no idea what's causing that issue in that case. It could be that it's some internal overvoltage protection in the DC to DC converter bricks that's kicking in. I think they're actually rated for 12 volts output, and we're pushing them to over 14, so it could be something like that. That the control board, out you come. That the control board is just feeding it to too much voltage, and it's just gonna keep kicking in forever. We could maybe, instead of doing the drudge work of replacing the caps on stream, we could maybe try and troubleshoot that and see if we can get rid of the annoying overvoltage protection issue. And I have a reasonable clue as to how we might go about doing that. Since on the control board, there's my right camera. Since on the control board we have, it's just easier to see the schematic really. Let's bring the schematic over. We can leave it zoomed in. That's our control board. So if the issue is that it's actually the DC to DC converter bricks that are triggering the overvoltage, we can fix that by limiting our voltage adjust setting, and we could do that by reintroducing R472 here to some extent. 470 ohms is going to be way too low. We're going to just get no output at all. But I think we have like a 10k. Is it 10k? Resistance 5k. We have a 5k potentiometer feeding this voltage adjust thing. So if we put like just a little bit of burden voltage here, burden resistance here, we can probably just limit our maximum output voltage a bit, enough to make it not trip the overvoltage protection. To figure out what that resistor should be, we want to measure the resistance between the input to the ISO and the voltage adjust pin here. So this is going to be J1 pin 7. This is J1 pin 1, 2, 3, 4, 5, 6, 7. Does that just go straight to, how do we get that? Does that just go straight there? It does not. So our input on the OPA on the ISO 92 is going to be pin 15. And I have no idea how they enumerate the pins on this thing. It's going to be... How many pins is this package even supposed to be? I have no idea. That's pin 1, is it? It's going to be like that one? Maybe? 100k? That's not right. 60. Ah, man. This is a bit... Oh, they bother. I have no idea how they count the pins on this particular chip. let's take a look under the microscope and just see if we can kind of trace it out a little bit. See if we can figure out where our input signal actually goes. There's going to be pin 7, which is there. It goes. There's R44, which is going to be that guy, which is 1K. So we're on the right track. That's in series, and it of course goes to a via, and then it goes to this bot resistor there, which goes to pin. It just goes to some random pad, which goes somewhere. Perhaps that's ground. We have ground on pin 8. Let's see if that resistor there just goes to ground. In that case, we'll probably have an input impedance of like 28 kilo ohms or something. So we have 26k in the resistor. And how do we even frame this? So pin 8 is going to be ground. Pin 7 is our input. That 37k. That's higher than I expected. And I'm guessing this is not just going straight to ground then. No, it's going straight to ground in series with probably this bodge resistor. Yes. Okay, so we have ground in this bodge resistor, which is in parallel with the other bodge resistor, which is going straight to our input, I think. If we measure from our input pin to the one end of that bodge resistor. Okay, now I'm just confused. There's one. Oh no, there's 1K there. Yes, so our input circuitry is we have R44 here, which is 1K going into a, you can imagine this is 27K, and then straight in there. So by reintroducing R42, we can just burden that down a bit. We don't want to, I'm going to say 100K. I think 100K ohms might be reasonable. It might be reasonable. Good guesstimate if we can figure out which is actually R42 on this board. It's not too easy to figure out. R42 there. Would it be this guy maybe? That goes to a capacitor, which goes to one end. It goes between this, which is our input, I think. And I think that's R42. So let's grab a 100K. Let's make it a bit more still. 220K. 220K ohms across there, and we'll see if that does anything. I do want like maximum possible output voltage out of this, so I really don't want to overcompensate. It's just annoying if these won't go above 13 volts. We just don't want that. So this is our 220K burden resistor, which is just going to go across there, load this resistor down, and as such lower the maximum voltage we're going to get across there. And as such, limit the risk of overvoltage protection kicking in. If that is what's happening. We still don't know if it's actually the overvoltage protection in the DC bricks that's kicking in. We just don't know. And I'm not bothered enough to figure it out, and if this doesn't work, I think I'm just going to leave it and put a big warning, OVP danger. On the board, because it's basically a spare board anyway. Like, the other boards probably work better than this, so I'm not too bothered. I would use a surface mount resistor, but I don't have a 1206 kit. I only have up to 0805, so I don't actually have anything that really fits here. That's why we're doing a through-hole resistor for the surface mount. Something like that. We'll just solder that in place and watch it go flying. Fan on. Pardon the screaming. Let's see, can we get this to solder? Ah, we got it to solder without going flying. Beautiful. And the other end as well. Okay, so that is a 220k burden voltage on R42, which is maybe, just maybe, going to limit our maximum output voltage swing. I'm just putting the board back off camera, sorry. And let's just shove it in and see what happens. Station 240 in chat asks, how are the power prices in your area now? Not good, but they're not catastrophic anymore. For those who are not aware, Europe has had some issues with electricity prices. It's been like 10 times more expensive than a usual year, which came as a bit of a shock. Anyway, let's see if this will work. We'll just keep turning this up. Slowly. 11, 12 volts, 13 volts, 14. Let's just use a proper meter to see the output voltage, because the cheaper eBay panel meters I put in these, they're not the best. 14.1. Oh well, you cannot see anything. There you go. 14.13, 15, 14.4, 14. Hey, we're maxed out. 14.56, and it's not turning off. And just to make sure it didn't have to do with me just going there fast. Nope. That's a bit on the low side. I'm quite sure we've actually figured out the issue with that. We were hitting a hardware over voltage protection inside the DC bricks themselves, since that did work and we still get a reasonably high output voltage. But I think I want to step that resistor down to like, let's do 330k and see if we can get just a bit more. All the other boards for these, they can put out about 14.8 volts without tripping the over voltage protection. So I really would like for this one to also put out 14.8 volts. That's just you know, it's enough voltage to decently boil the lead acid battery, which is like 50% of the use case for these things. Right, 330k. Let's use our lovely zip tie to actually rip this out now. It's still not easy because we have this like giant backplane connector in the back. Ugh. And we still have all the voltage in this. Like this connector, it's a big chonker. It will not come out easily. Right, well, we're not working on the big board, we're working on the control board. That's what we're interested in. Right. We barely even need the microscope for this. It's a through-hole resistor on a 1206 pad. We'll just bend these leads suitably. So this is going to just reduce our burden voltage just a bit. Burden voltage, burden resistance. Have I said burden voltage all this time? Oh no, I'm terrible. Right. This is where I rub my hand up against the power board with like hundreds of volts in it and go flying. That's not beautiful, but it's on there, I think. Yeah, well, that's actually not that bad for a solder joint without fresh solder or flux. So let's just poke that in there again and see what happens. Oh Jesus, when did we get 218 viewers? That's like 10 times my average. Oh no, we don't. I'm fooling myself. We have 7 we have 7 viewers. We have 218 playbacks. That still doesn't usually go that high. Lots of people having nothing to do tonight. Oh man, that's an embarrassing mistake to make. Jeez. Good. I don't want to be seen by 200 people. Anyway, let's get that back in. And see if it's going to work better. That's the best voltage view you're gonna get. Sorry. Yeah, it's the usual number of views. I was being an idiot there, looking at the wrong numbers. Let's see how high we can get. $14.2, 4, 5, 6, 14.7. So we're definitely on the right track. 14.7. I want 14.8. And we clearly have a bit more headroom, so let's just step up to 470k. 470. Maybe we want to do, let's just do 560k right away. Oh. We gained about no, we want to do 470k. We want to do 470k because we gained about 0.2 volts or so by going up by going up 100k. So we'll do 470. I think that's gonna. This might be slightly too much, and we might have to settle for 14.7 volts output. But we'll give it the honest try. We'll give it the honest try. Put the board somewhere. My workshop is just 1/10 the size it should be for what I'm trying to do here. Okay, let's just put the schematic aside so we don't just make a mess of it. I don't think we need it anymore. And let's see if we can just rip this out quick and easy. So we'll heat that hot. There we go. So you're going to have to place your bets if this is going to work or not. I'm kind of suspecting that we're going to get the over voltage protection kick in again. Because I've never seen one of these do 14.9, which is what I think we're roughly going to end up at with a 470k resistor. Let's put some fresh solder on there. There we go. 470. Rob G says, you mentioned TME earlier. I ordered from them for the first time this year for a project I'm super proud of because I wanted specific on-pair switches they stocked. Amazing fast shipping to Finland. Yeah, TME are good. Generally nice to deal with. Their webshop is weird and strange, but generally pleasant. If you have a big enough order to satisfy the like €25 shipping, that is. But that could be an issue that's specific for my area. Like you cannot get shipping that's cheaper than 25. At least I can't. But for any order over like €200, who cares? Okay. Let's see. Oh, we're maxed out and it's still working. That's good. What do we actually have? 14.8. I think trying to go higher than that is going to be stretching our luck. Because we're dividing, like we have a 37k to 470k divider. It's like a 10-to-1 resistive divider. So going further than that is we're getting into the no resistor installed at all territory, and that we know that causes issues. So I'm going to call that a good enough modification. We're getting enough voltage out of this thing. I expect 14.8 out of these, and that's what we get. So now the rest is just going to be a question of dreary general restoration type stuff. Rob G says TME ships for €9 to Helsinki next day. Yeah, that's different than what I get, that's for sure. But you know, Åland Islands, we're special. We're not EU, so everyone hates us. Everyone hates us. Right, so I mentioned we had a bit of a burn on the other board, and right around here. That's because of this resistor. This is a 22 ohm resistor straight across the output, which is absolutely fine if you're putting out 5 volts. It's not fine if you're putting out 15 volts because you get 10 watts in it. It's not necessary if we're going to get rid of that. We just really want to get rid of that. So we're done with all modifications now. It's just a question of restoring the board, doing general service. God only knows how many hours these have on them. It's also annoying to have a 22 ohm resistor across the 8, but if you leave something connected to it, for instance a battery, because you end up with a warm power supply and an empty battery. This board is very heavy duty copper, so heating this just takes forever. Okay, I think we need to just put the giant tip back on, because this is not doing the thing. Big tip. Right, big tip. Let's go. Yo. Let's try to burn our fingers. Come on. You can do it, I believe in you. 15-year-old OE soldering iron. This is ridiculous. This resistor is just not coming out. Okay, fine, we're just snipping the lead, jeez. I give up, okay. There's just no thermal relief on the solder pads here, so we're just heating the entire board area through the via, and the via just cannot carry enough current, enough heat to the top side of the board to actually melt the solder. So we're just going to end up slowly overheating the board, which isn't good. So that's that taken care of. So now it's basically just a question of replacing a few caps and then we're done. So this capacitor is a bodge. You can see because they haven't actually put a trace to it, they just put a piece of wire like that, which is not a very good way of installing a capacitor. We're going to replace it with something better and also mounted better. That's one end out, and here I'm not sure how well you can see that, but they've just scratched a bunch of copper off of this trace and drilled a hole in the PCB to mount the cap. And there is out. Old ROE cap, they are notorious for going bad. Oh, that's evacuated. We do not need this jumper anymore. Be gone. So this is a row of 10 microfarad caps across the 8, but I've just replaced those with a few different values. Since why not? Different value capacitors give you a bit of a different response. So you get some that take high frequency noise, some that take low frequency noise. And you know, that's what you want. Let's reframe this a bit. Crotch cam. We cannot avoid it because I need to work outside of the boards. Outside the bench. Let's preheat this board just a little bit because it's just super high thermal mass stuff. Ripping these caps out without preheating it's It's close to impossible. I've done 3 of these boards already, so I would know. The thermal mass is not to be underestimated. There we go, that's going to be something like 100 degrees, or at least 70. Rob G is asking for my email. My email is ffcossag@gmail.com. As in channel name @gmail.com. So this is a small green film cap which we need to get rid of because it's going to be in the way soon. Very hot. And the rest of these guys are electrolytics. I am burning my fingers. One electrolytic. Ow, ow, ow. Very, very painful. A 3. Oh, that guy came easily. And now we need to actually evacuate these holes as well. That went way better than the other boards have. I think these are nice and clear. Yes. Huh. Nice. Now, since these are old German caps, which have a tendency to last for 40 years and then just kind of cease, I'm going to clean the board up with some isopropyl alcohol because there's always a bit of capacitor electrolyte residue underneath these. Yeah, that's just not what you want underneath your new caps. And let's just copy the arrangement from the other board. So I think it's like 10, 22, 47. And it's a bit picky which of these pins are actually soldered, which of the holes are soldered to, because some layout considerations. Yeah, let's do 47, 22, 10 microfarad, and I have prepared a bunch of caps here. So we do good practice, pre-bend the lead so you don't cause any bending inside the gasket. That can cause premature failure. Let's just put this board right side up so I can copy the layout. And this should be a 22. Bendy leady. .22 and a 10 microfarad. And I forgot to bring out, but we also want a replacement 1 microfarad there. 1 microfarad. Like so. And kink the leads on the underside so they don't just instantly fall out. And we can flip the board over and solder those. And before we do the other side, I need to run to the other room for a second and check on a thing. You get exciting house walk noises. There we go, had to adjust a fan for heating. Right, let's just keep soldering. There we go. And now you can get to enjoy the miracle of the TR30A, which has this little metal clip thingy for catching leads. So look at this. We have leads here. They're stuck to the pliers. Hard. They didn't go flying into my eyes. This is amazing. We can repeat that. One hand. And the lead stuck to the pliers. It's amazing. One hand. No fire. Like, I have an instinct to always grab the lead like that, or just look away so I don't get launched, but I can just look at it without getting my eyes shot out. It's absolutely lovely. Amazing invention. Right, so we still have a couple caps to do. These guys were just 10 microfarad for some other purposes. And the guy that's still in the same row as the others is oriented the other way around. I know that because I found it out the hard way, like one of the first ones I did, because I just replaced the entire row in the same direction for the first time, and one of the replacements, it ceased to be a capacitor rather quickly. It was exciting. A bit exciting to desolder this so close to the leads we just soldered in. There we go. And yes, this thing cracked and it's held together with a zip tie and super glue. I need to order a new one. But it still works. It's kind of keeping in one piece. So that was another 10 microfarad. Which we will pre-kink the leads on. Like so, and then we have this guy over there. Zeke himself says, "Hey, late again. Yeah, you missed all the exciting schematic reading earlier." I'm really happy with the presentation we got out of a schematic reading. I felt like I was having a lecture in front of a classroom of students. It was nice. It was unusually high quality content for this channel. Oh shit, I almost forgot which orientation this guy was in. But it's a negative side towards the connector. Negative towards the connector. And that's another 10 microfarad. Like so. Now let's just demonstrate the amazing thing that is the Pierre Giacomi TR38 to Zeke himself as well. It has the lead grabby thing. It grabs the lead. It grabs the lead. Ah, beautiful. Oh, we have more leads to solder. I almost forgot to solder the other cap. Oops. There have actually been times when I've been working on a board and when I've like assembled everything and gone to the customer to install it, I have noticed that I have an unsoldered component somewhere on the board and I just have to sneakily pull out the portable soldering iron and solder it in place and cut the leads before I install the board. And just be like, yeah, it was a bit difficult to access, ma'am. That's where it took a bit longer than expected. Hoping that I don't get walked in on just soldering on the board on the tumble dryer or something like that. It's sneaky technician things. Kyle Villor says, Windows picked a lovely time to update my audio drivers. That's why you just don't run Windows, at least not Windows 10. Okay, so that's going to be most of electrolytics, save for the big one. So we previously had the big capacitor, like so, variated frame. It was like that, I think. And that's going to get replaced with this. And it's going to go in that hole, and I don't remember which other hole. Which hole does it actually go into? Oh yeah, it goes into the sneaky hole there, which is for the old capacitor. And that's actually really sneaky because they haven't really... They've drilled a hole through this trace actually, but they haven't scratched it, so it's impossible to solder. Oh well. It's been fine all this time. I don't think we need to solder it. So we have the positive for this cap in that hole and negative in that one. That's why we had to remove a little green cap which was there. So we'll just kind of shove this in there with violence. There's no good way of mounting this cap, since it's an afterthought even from a manufacturer's side. We just sort of, yeah, yay it in like that and glue it afterwards. You know you've mounted a cap well when you bend the lead inserting it. Blobbity blob. I'm using a 2200. Oh, yeah, it looked like. I know this is a TR38. I'm using a 2200 35 volt cap on the output. Just the original was 1000 microfarad. I just wanted a little bit more oomph and a little bit better transient response on this thing. It can actually shut down fairly easily if you just short the leads and it just overcurrents. The Never Sleeper says, "Hey, FFcossag, I just got in from an 8-hour shift. Great to see you doing live streams." Thank you. Great to see you watching. Not that I see you. Zeke himself asks, any chance we could get live streams that aren't rec stream quality uploaded to a secondary channel? Pretty please with sugar on top. That's a bit annoying because I don't think this PC has the grunt to encode video while streaming video. Like, this is literally a 6600K without a GPU, and it's so full of capture cards and stuff that it's annoying to put a GPU in it, and I am not paying for a GPU right now. If someone wants to send me like a GTX 750 or 1030 or something, sure, but I don't think anyone wants to do that. So if we just have a couple more caps to replace on this, these guys which are 470s and these which are more 10 microfarads on the secondary of these positive and negative 12 volt regulators. The Never Sleeper asks, what are you planning to use the transmitter for? This is just a part of a transmitter. I am not planning to use a 50 kilowatt analog TV transmitter for anything at all, because I don't own a radio tower and analog TV doesn't exist. I'm just using these guys for big, beefy, adjustable power supplies. They're just big, good power supplies for general purpose applications. I am trying to find a 470 35 capacitor. I know I have bought roughly 1 million of those, but I keep misplacing them. Like, it's one of those things I've bought so many of them so many times that I just know I have them somewhere, but I keep losing them, which isn't good when you need them. Bloody hell, I know I have 1,470,35. What is this? I'm just desperately digging through my component cabinet. Do I have a 330? Above there, that would be a step down. I would have to use a 680. We have 680s, but seriously, I should be able to have a 470 microfarad 35 volt capacitor. Yes, good. I found 470 microfarad 35 volts, like the most standard capacitor after the 1016. Good. Right, now I'm going to put this right there and forget about it for a year. And then the next time I'm looking for it, I'm just going to keep searching forever. Right. Zeke says, fair enough, Chief, it's just my FOMO for stuff like the drunk live stream I only caught a few minutes of a couple of weeks ago. Well, the drunk live stream I was like intentionally not recording for publishing, because I knew I was gonna like basically just act an ass on that stream, and I didn't want to think about what I really said. Let's see which direction these caps go. Negative toward the transformer. negative toward the transformer. Okay, I can't do that. We need a bit of solder on that to just melt everything. Okay. So we put our apparently very difficult to source caps into those holes now. Chat is saying all kinds of things. Kyle Valor says he's still running an Intel 4820K CPU. My main everything PC is a 3770 with the 1066 gigabytes, and I'm probably gonna run that for another 10 years. It's fine. I deal with hardware upgrades by just not running new terrible software that I don't want or need. Negative toward the transformer. Solder base. So this is the logic power supply, like what we're working on right now. It's the logic power supply for the control circuitry and stuff. And we can keep using the pure gear Komi. Ah, I love this thing so much. This is just like there's a little in my body every time I snip it and it doesn't go flying. And now we have these guys left, which have negative in opposing directions, but they're actually marked, unlike most caps on this board. And we are replacing these 10 microfarad caps with 47 microfarad low ESR caps. It's just on the output of the linear regulator, so it doesn't really matter. But I think one of these regulators actually powers the fan, which I put on these boards. So I want a bit more grunt out of these regulators, and I fear that running the original 10 microfarads, it just might cause a bit of ripple, since computer brushless fans are kind of notorious for pulling current in horrible jagged waveforms. And horrible jagged waveforms are not good for delicate control circuitry. Mortia 38, pawn. Ah, so good. So good. Okay, I think that would be all the caps we are going to bother replacing. So something really cool about these boards, or these transmitters in general, is Itelco actually made their own capacitors, and they called them Itelcond. I just love that. Like, Itelco makes transmitters, Itelcond makes capacitors. That's just beautiful. I have no idea what these actually are. They don't seem to be going bad, so you know, it's fine. Dated 19th week 97. All right. I think we're basically done. I would like to put a fan on this, but I really don't think I have any suitable 120mm fans lying around. I think I used up the last one I had doing the other board the other night. I mean, I have 92mm fans, which I think are just way overpowered and not really worth putting in there. I don't want to put some like ridiculous fan that's going to use too much power, so yeah, I'm just not going to be putting the fan on this right now. I'll wait until the next time I buy a bunch of fans and put something proper. Something like the Arctic F12 TC, which is on this, which has automatic temperature control. So all that's left to do now is... we are missing two components. We are missing two components because I still want a couple of extra bypass caps. Tiny ceramics, these guys, because they have a tiny bit of high frequency noise, these guys, in their default configuration, and it's just putting two 100 nano ceramics across the output just basically kills that completely. I had two ready at hand. I now only have one, so I have to fetch another one. Let's put these 470 mic caps back where they're supposed to be so I can forget about them again. Okay. Another 100 nano. Let's get that mounted. We can do it under the microscope. I still need to get a better microscope camera. So we have a cute little holes that we can just use for this, really. If we cut this, the leads of this to a reasonable length, we can just poke them in there and fold it over. And it just lies down flush on top. Come on. Get bent. There we go. Beautiful. That's going to be a needlessly strongly mounted 100 nano ceramic. There are no leads to cut on that. The other one we're putting straight across the output. Hey, I haven't soldered that quite properly. Let's fix that first. There we go, properly soldered. Where did the other... Oh no, there. The other cap is, of course, right on the board, exactly where it's supposed to be. So you're just going to go like that. Something like that. There we go. Beautifully mounted. And now we can use the TR25 to cut this, since we don't need the lead catching, it's just going to get in the way. And there's our extra little bypass caps installed to just take the edge off of the final little ripple. So, yeah, someone was really surprised that I didn't have any spare 120mm fans. That's the way the cookie crumbles sometimes. Oh, I should actually reflow the current shunt here, because that runs really hot and the solder doesn't really like that in the long run. So we'll just gob a shit ton of solder on there. Just to make sure it doesn't crack with time. Wait for a decent amount of time for that to cool so it doesn't just fall off when we solder the other side. There we go. These wires are not melted into each other. I think this is basically ready to go. We'll just put the control board back and put it back in the case, and I guess, well, we'll give it a test run. I can't put it in service yet because, well, no fan. But that'll sort itself out eventually. This board's in its final iteration, so we can just screw it in place. If I can find the screw, which I seem to have placed in a suitable location, so we'll just take some random M3 we've found on the bench. Maybe it's the original one, who knows. Zeke himself says, oof, that second leg on the second cap looked cold. Nah, it's fine. It's absolutely fine. Solder joints tend to look really bad under the microscope because the way the light reflects on them, they like a row of lights on the joint often looks like a crack, but it's just like the super stark contrast which this stupid microscope camera can't pick up properly. I also want to put this little screwy nut thingy back into this hole because it actually presses up against a metal thing and helps hold the board in place. There we go. Alright, time for, I believe, a final test before we're going to end the stream. Here we go. That's poked inside. Let's let's give you guys an ever so slightly better view. Something like that. I'm not going to try and change the angle of the camera because that's just going to take 10 minutes. Power goes in. Power goes on. We have voltage. We don't max. We don't OVP, even if we really just ram it to max. No OVP. Good. And our voltage is, these meters are just complete garbage. 14.7 means 14.8, but cheap eBay panel meters, who cares? So let's make sure we actually get our full rated current out of this thing, which should be about 45 amps. So it feels really stupid to do this, but 47.8 amps. That's working beautifully. .6 volts at 47 amps. And my 4 square mil cable is getting nice and toasty. We probably have like 50C inside the rubber, so let's not do that for too long. We don't want to cause a fire. So I think we're done for the time being. We have turned our unmodified board into a modified board which works. I now have 2 working spares for these guys, which is, well, all I'm ever going to have, because I doubt I'm ever going to find any more of these boards ever again. Although one important thing remains to do, and that is to document our progress. So modified, (2022-01), and that's a 40 amp board. So as these boards age, more and more of them are just going to get this 40 amps crossed over, and it's just going to say 20 amps. Since they are going to be blowing drivers every now and then. That's just unavoidable with this sort of thing. So this guy is a 20 amp board, since half of the drivers there are just broken and blown. I don't think there's much. Oh yeah, we can't actually keep this board in here because it has no fan. It's going to turn into a 20 amp board and a 0 amp board rather quickly, passively cooled. Well, these DC to DC converter bricks we have underneath the heatsink are fairly efficient. They're not that efficient. They do need the fan. And this, you can see the big honking isolation transformer there, which we shouldn't be poking around though with the power plugged in. This honking isolation transformer, it's only about 500 VA. It basically saturates under full load, so we do need a bit of airflow across it as well, just to make sure these things don't smell too much like hot transformer while they're running, which they do. If you load these down at like maximum power output, they will smell a lot like a hot transformer while they're running. Right, come on, in you go. These brackets are a bit annoying. I love how I was able to create a completely compatible mount for these, by the way. Like with a fan and everything, all the like aftermarket things being completely contained and mounted on the one single connector. There's no wiring, no spaghetti, no annoying stuff. If you want to swap a board, you rip one out, you plug one in. It's that easy. I just love making systems like that. Even when they don't quite want to fit the racks. Wait, that's for 20 amp. We don't want the 20 amp board, we want the 40 amp board, which is over there. We want the 40 amp board. Ugh. Come on. Quit being annoying. There we go. The 40 amp board. And the little screen thingy. Just to save our delicate fingers. And the front panel. There we go. Much better than new. How much voltage do we actually get out of this one? 14.7. So, hey, the new board is better. We get 14.8 out of that. Lovely. But we're going to end the stream there. We've been going for, my throat tells me, all night. So I'm going to have to thank you guys for watching. Cheerio.